So it looks like it'll be a while again before I can get on the network here. So I put up a thing on Piazza if you have questions where you could type up your question and then I'll answer it in class. Just a couple of administrative things. There were a few people who, that's interesting, who didn't turn in their homework, and who later told me, well, I got something done, but it wasn't good enough for me. And the winning strategy is to turn in what you have. Maybe you'll get partial credit. And at any rate, if I look at the graders report and I see that a whole bunch of people tried but didn't do well, then maybe I get some feedback that next time I should make the homework easier. But if I just get a bunch of feedback that says people didn't even bother to turn anything in, then I don't really know what that means. So turn in what you've got. And if it's all terrible, then we'll deal with it. The other thing is, I still get people who say, what can I do? I'm stuck, and I say, just put your broken code on Piazza. And people say, really? I can do that? I'm allowed to put on code on Piazza? Bring it on. If there's code that you have that is not working, copy and paste it into Piazza. Try to explain what your question is. Say, I'm trying to achieve this. This is what my code is. It's giving me this horrible error message. And then people will be helpful. People have been super, super helpful on Piazza. I'm really grateful for those people who've provided answers. And there have been lots of dialogues where someone asked a question and 3 or 4 steps later the resolution was, oh, now I understand. Oh, now it works. So it'll work for you too. Just bring it on. The third question that people were confused about is, can they submit multiple times into the Dropbox? You can submit as often as you like. And so the grading script will go through all of the submissions that you have and pick the worst one. No, it'll pick the latest one. And so the latest one is the only one that it looks at. So that means on Saturday, like noon or so, you should be having some solutions up there in the Dropbox that are hopefully pretty good. Because let's face it, it's difficult to make predictions, particularly about the future. So how do you know whether the internet isn't going to completely flake out between noon and midnight? So put something up there at noon, and then you have it there. All right, so let's get going with the lecture, and then I'll take some questions a little later. So I'm going to be talking about recursion, and so there's this little motivating example that about triangle numbers. And just because it's visual, it's nice, it's easy to understand. So the example is to compute the area of a triangle like that, where every square has area 1. And so we make a triangle object, stash away the width from the constructor, and then we have this getArea method. And we're doing it in this recursive way, which, if you haven't seen it, is kind of the lazy man's way of computing. So we'll say, let's handle the really easy case. Let's say the width is 1. In that case, the area is, of course, 1. And so here's the code. Well, what if it's bigger? Well, so we want to compute the area of the big triangle here. And now we're going to make a crazy assumption. We're going to say, well, someone else surely knows already the area of this littler triangle. And if I ask that someone else, hey, what's the area of the little triangle? And then I add just the 4 to it, which is the width of the triangle, then I get the width of the bigger one. And so that's the way to do it. Now, how do I get the area of the smaller triangle? Just make one and ask it. So we're making the smaller triangle, and we're asking it, hey, what's your width? And so the thing that makes recursion work is that we're just going to assume that somehow the answers to all simpler, easier, smaller problems are already known. And then we make use of that to compute the answer for the bigger one. Now, of course, what's really happening is that when one makes it when one computes the area of a triangle with width 4, that makes a triangle of width 3, which also doesn't know what its area is, so it makes a triangle of width 2, which also doesn't know how big it is, so it makes a triangle of width 1, which does know that it has area 1, which then tells the next one, which says, oh, I must have area 1 plus 2 or 3, which tells the next one that I have area 3 plus 3 or 6, which tells the big one that it must have area 10. And now here comes the most important part of recursion. Don't think about this. Everyone who thinks about the thing getting smaller and smaller and then coming back is just confusing. The correct way of thinking about recursion is to say you just want to be lazy. So you say, if it's real small, I know the answer. If it's big, I'm going to break it up into a smaller one, and I couldn't care less how the smaller one knows the answer. Maybe it rearranges cornflakes on the dining table. I'm just going to ask it, and then I'm going to put together my answer from the smaller one and the piece that I know. So in this case, just by adding them up. And that's a very, very powerful idea, and it makes lots of programming very simple. Lots of times you have problems where they very naturally fall into this kind of decomposition where you say, do the real easy thing, and if it's more complicated than that, then break it up into subtasks. Don't worry about how those subtasks happen. All right, so that's the basic idea. And as long as you don't think about it, it's easy enough. A couple of things that you need to pay attention to. Number one, you have to have special cases for the simplest situations. So usually that means size 0, size 1, maybe size 2. You need to manually say how the solution is arrived at, because as the problem gets smaller and smaller, at some point you hit those smallest cases, and those just must be done by hand. But no big deal. It's always easy to deal with those easy cases. You just need to remember to put that branch in there. And so the second one is that you must somehow, if you have a complicated input, you must somehow manage to make it simpler. So for the triangle, the insight was to say that when you have the big triangle, come on, here, when you have the big triangle, the insight was that if you lop off the stuff at the bottom, then the other thing was still a triangle. And that insight is different for every recursion problem, and that's where people have the hardest time with usually. And if you have a specific problem to see, how can I break it up into something simpler? I have a lot of questions on Piazza about recursion. All right. Can I finish this module and then we'll do Piazza? All right. So there is one thing, though, that I should say about the example with the triangles. It was only there for motivation. It was only because the triangle is easy, it's nice, it's visual. It's not exactly a great example of where you would use recursion in practice, because it's actually perfectly easy to compute the area of a triangle with a simple loop. So you could set up. Now this is 1, this is 2, this is 3. And so adding up 1 plus 2 plus 3 and so on can be done with a loop just like here. You don't need recursion for it. And in fact, you don't even need a loop, because it's well known that the area, that the sum of all numbers from 1 to n is n times n plus 1 over 2. So you could just compute it directly like that. So it's a motivational example, not one for where you would use it in practice. All right, so let's have the first clicker question here. So here I'm having a shape that's almost like a triangle, except it's called a mystery shape, and again it stores its size. If the size is 1, the mystery shape has area 1. Otherwise, I'm going to take the mystery shape and cut it in half. This time I'm not subtracting 1, but I'm cutting it in half. I'm asking the smaller shape, hey, how big are you? I'm now multiplying that by 4. Then for technical reasons I would see later, if the size was odd, I'll make an adjustment. That won't happen for you in this case. And then I return the area. And so my question to you is, what is the area of a mystery shape of size 4? So go ahead. You'll probably need a sheet of paper. I wasn't able to do this in my head and figure it out while I fire up Piazza. All right. What's that? Oh, no, option D. So let me see if I can still fix it. Anyway, D is not the right answer. If you think it's D, try again. Yes?
Isn't the answer 32?
No.
So it is 4 into 2.
No. Okay. All right. So let's just do this together. This is not an easy thing apparently. So the size is 4. So we have a mystery shape of size 4. Then it says over here, make a smaller one of size 2, compute its area, and multiply the whole thing by 4. So I put this together here 4 times mystery shape 2 get area. Now let's see what mystery shape 2 get area is. Well, then we cut it again by 2, so we take 4 times mystery shape 1 get area. Everyone with me? So mystery shape 4 turns into mystery shape 2, turns into a mystery shape 1. What is the area of a mystery shape 1? It's 1, right? So you see that here. So we know that this thing here is 1. What is the area of a mystery shape of size 2? That's at this level here. It's 4, because we take 4 times mystery shape 1's area. And what about the mystery shape 4? So here the answer is 4. So then it's 4 times 4, or 16, right? And now is my real question. What is the mystery shape? It's a square, right? Because what I've done is this. Here's my mystery shape. And I said, gosh, I don't know how big it is. So I cut it in 4 pieces. Come on. I cut it in 4 pieces like that, each of which is again a square of half the size. And so the area of the big one is 4 times the area of the little ones. The only time that I had to worry about it a little bit is, what if its size was odd? And so then actually what I have to do is I have to take out the middle strip like this, and then I have 1, 2, 3, 4 smaller ones here, and then I have to add in the middle strip here. That's what happens here. So this will accurately compute the shape of a square, which again you could easily do without recursion. But it shows how the recursion proceeds. And it shows that you have to have the ability, with a recursive call, you have to have the ability to trace it. So the only way that I know how to trace it is by writing down the intermediate answers. If you just try to do it in your head, it's too confusing, particularly once you go beyond 2 or 3 steps. All right, so let's see what other questions you have on Piazza before I continue with the lecture. Okay, can I go over this quiz question in class? I'll be glad to. So, why is the answer an exception will occur? I have no idea. Why would that be the answer? What's the difference?
With minus 1 and with plus 1.
But over here it does say with minus 1.
It's saying replace it.
Oh, it says replace it with a plus? Oh, yes. Thank you. All right. So, yeah, let's see what happens. So let's say this was a plus. Let me try to make this a little larger so one could actually see this. So this is a plus here. And now we'll start with a triangle of size 4. And now what's it going to say? It's going to say, well, now make me a triangle of size 5 and ask what its area is. That's going to say, oh, I don't know. What am I supposed to do? I'm supposed to make a triangle of size 6 and ask that what its area is. The triangle of 6 has area? I don't know how to compute my area. Let me see. Oh, I need to make a triangle of size 7 and ask that what its area is. And that process will never stop because your triangles are getting bigger and bigger. And so actually it will stop eventually because all of those computations that are pending, that are still hungering for the answer from the next guy, all those computations need to be stored somewhere. And they're stored on an area called the runtime stack. And after so many tens of thousands or millions of recursive calls, eventually that area will overflow and your program will die with the stack overflow. And so that's the exception that they're talking about. And so that's a common problem, that when you set up the recursion the wrong way, when you make it so that things don't get smaller. Now, few people set it up wrongly this way. I mean, why would you make the triangles get bigger and bigger? But what sometimes happens is that people keep the size the same. They forget to cut it down. And then you would still have the same effect. So if a triangle of size 4 makes another triangle of size 4 to ask it how big are you, which makes another triangle of size 4, then you would still have the same effect. So it is a common error. All right. Now the other one is with this fib thing. Okay, so that one, let me get up a piece of paper. So we have this function here that we'll see actually on Thursday's lecture in more detail. So fib of n is fib of n minus 1 plus fib of n minus 2, and with a special case that fib of 0 is 1 and fib of 1 is 1. So let's compute fib of 4. Well, I have no idea what it is, but I know it has to be fib of 3 plus fib of 2. What's fib of 3? Well, how would I know? It's fib of 2 plus fib of 1. Well, the good news is I know what fib of 1 is. That's 1, because that's the special case here. Do I know what fib of 2 is? Well, I don't know what that is, but it's fib of 1 plus fib of 0. And I know what both of those are. They're both 1. Now here I have another call to fib of 2. Now the computer has no memory. It doesn't remember that it made the same call before. So it's going to execute it again, and it's going to say that's fib of 1 plus fib of 0. So this is 1 and this is 1. And so how many calls is it making? Well, let's count them. 1, 2, 3, 4, 5, 6, 7, 8. So it makes 8 calls. Is there any way to get this answer without drawing this very picture? No. So the only way to answer a question like that is to get out a sheet of paper and to write down in boring detail what calls what. There is no shortcut to this. So every time that you have one of these mystery recursion questions, that's what you've got to do. Get out a piece of paper, keep track of what the intermediate calls are, what calls what. And if you don't do it on a sheet of paper, it's unlikely that you'll be able to keep it straight in your mind. So that's the trick to do this. And the answer was 8. Good. Now, in all honesty, sometimes when they make these multiple choice questions, it's a little ambiguous. Was this meant to be a call? But the designer of this question was smart enough not to offer 9 as an alternative. So one didn't have to parse the question text so carefully. Okay, moving on here. This is homework 3. I'm going to not do that in class. Yeah, now this one here was a question that had a bug in it. So the correct answer is to return 1. So let's understand this one here because it's actually a nice example. So we have a method that computes x to the n. And so the lazy way of computing that is, of course, to say that's the same as x times x to the n minus 1. Except we have to stop somewhere. And so we can stop if n equals 0. And as you remember from calculus or wherever algebra, x to the 0 is 1. So here it does have to return 1. Now I realize that for whatever reason, the quiz said that the correct answer was D, or 4. And that was a bug in the quiz. So once in a while these quizzes are buggy. There was a discussion about that like yesterday morning. Someone posted that. So I wish these quiz questions were perfect, and unfortunately they're not. They get outsourced to the Bahamas or somewhere, and what comes back is not always right. So when you find an error like that, put a question on Piazza, and also be on the lookout for complaints about buggy quiz questions on Piazza. Like I was very gratified to see that people were doing it yesterday during the day and not at 11:50 p.m. So thank you, because that gave everyone some time to recover from this. All right, question. Let's see if we had another one here. Okay, we did this one. We did this one. Okay. Did I miss one? Okay, let's see. I need to make this smaller so I can read it. All right, so here someone asked about the puzzle, and I don't begin to understand the question. So the way these puzzles work is that you can have them of any form. So you can have AE39QR plus BZ72QS equals, whatever. They can be as long as you like. Actually, that's not right. They can only be up to 2 billion or so you don't have to worry about integer overflow. But otherwise, there could be anything. There could be 1 letter, 3 letters, and it doesn't matter. The algorithm is the same either way. So let's have a quick look at the puzzle. Let's take a simpler example than this. So let's say we just have A, B, C plus 3B, F equals 4B, A. And I have no idea whether this has a solution or not. And so we want to solve this recursively. So this is an instance of type puzzle, so it's an object that has these strings in it. How can you make it simpler? So what could you do to this puzzle to make it into a simpler puzzle? Now it's not a triangle, right? So you can't deal with the size of it. So there's got to be a different notion of what it means to be simpler. Yes.
We try shortening the length.
So could we shorten the length? Could we somehow maybe lop off like a few of these characters? And yes, you could, but the problem with that is it would be difficult to take a solution of this thing and turn it back into a solution of the original. And so that's not what I'm suggesting in this assignment what you do. Instead, what you should do to simplify it is to reduce the number of letters in it. And let's see, how can we reduce the number of letters? Let's pick a letter that we never liked. I never liked the letter B. It's such an unappealing letter. My apologies to anyone whose name contains one. So I want to ditch the B. But of course I can't just ditch the B. I have to do something. I have to replace it with a number. With which number? 1. Sounds like a good choice. The truth is I don't actually have any idea which number, so I'm going to try them all. I'm going to make 10 puzzles where I replace it with 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. And then I'm going to ask each of those 10 puzzles to solve themselves. They're simpler. They have fewer letters in it. Each of those is going to labor mightily to find a solution. Let's say I replace this with an appealing number. 6 is kind of an appealing number, right? So let's say we have A6C plus 3,6F equals 4,6A. That's one of those 10 puzzles. I'm going to ask it, solve yourself. Be a man. And what's it going to do? It's going to say, well, I want to be simpler. And it's going to replace one of the letters. Let's say the A. And it's going to replace it with what? Well, it doesn't know, so it's going to replace itself with all of the numbers that are not already present here. So it's not going to take the 6, but it might take the 7. And so we're going to take these things and turn them into 7s. And now my puzzle is going to be 7, 6C plus 3, 6F equals 4, 6, 7. Yeah. I guess. Sure. So now you have a puzzle that is even simpler. Look, it only has 2 letters left. After a couple of more steps, you're going to have a puzzle that has no letters left, such as 7, 6, 0 plus 3, 6, 1 equals 4, 6, 7. Can you solve this puzzle? Sure you can. You add up the 2 things on the left, and then look at things on the right, and your answer is either going to be a strong and forceful yes if they match, or an equally strong and forceful no if they don't match. You have just solved this puzzle. You can solve every puzzle that has no letters in it and say with certainty, yes, it has a solution, or no, it has no solution. Okay? And then going back, that solution, if this puzzle says no, then of course the previous one is going to say, well, it has to have a few more tries, right? It has to go through the other combinations too. And if they all failed, it would say no. But if one of them succeeded, it would say, hey, I have a solution. And then it can report back to the previous one, either whether it has a solution or that it has no solution. So that's how this whole thing works. And so in this case, simpler means not shorter, it means fewer letters. And if every time we take away one letter and replace it by a number, if every time we do that, eventually we must go down to 0. And that is the miracle of recursion, that integers, when you make it by one smaller, eventually you have to hit 0. Even if you had a puzzle that had 10 different letters in it, you simplify it into those that have 9, that have 8, that have 7, that have 6. Eventually they must get to where there's no letters in there anymore, and you can just do it by hand. Now, it is true that the amount of work here does get pretty large because there's so many puzzles that are being created. But so what? As long as every one of them is solvable, then it'll work itself down to 0. So when you run it, you can imagine just how many puzzles get created. It's kind of amazing. But the code is very, very simple. All right. That should answer the puzzle. Okay. Is there a reason for, this is a great question. I totally love this question. Is there a reason in the triangle example to creating a new object and then calling a function on the new object as opposed to just calling a function that calls itself? And so kind of the standard way that normally people introduce recursion is like this. That you would have a function like the factorial function. So factorial of n is 1 if n is 0, and it is n times the factorial of n minus 1 if n is greater than 0. So for example, if the factorial of 4 is 4 times the factorial of 3, which is 4 times 3 times the factorial of 2, which is 4 times 3 times 2 times the factorial of 1, which is 4 times 3 times 2 times 1, the factorial of 0, and that's 1, so that's the answer, 24. And that's fine, that's a perfectly good recursion, but somehow when many students, when they see this the first time, they say, how can a function call itself? It's impossible. And so by doing the thing with the triangle, what I've done is, here I have this triangle. Now it's a big triangle. Let's call it Fred. It doesn't call itself. Instead, it makes a different triangle. Let's call it Barney. And it says, hey, Barney, what's your area? And so the hope is that when a student sees this for the first time, that it seems less implausible. Because it is, after all, a different object. And it seems more plausible that that different object knows the answer than that a function knows the answer on an easier input. But in fact, the two are completely equivalent. Because all I'm doing here is I'm really, the function calls itself just with a different input for the implicit parameter. So sometimes a problem is, it's easier to think about the problem in terms of objects. Take an object, make it into a smaller object. Sometimes that's very intuitive. Sometimes it's more intuitive to have a function just call itself with simpler inputs. And it really depends on the problem. Like with the triangle, I think it's very intuitive to say, let me make a smaller triangle. With a puzzle, I thought it was pretty nice to say, let me make a smaller puzzle. Because that way, I have my original puzzle here, and then I have the smaller, well actually 10 smaller ones that are sitting somewhere else. And to me, it seemed more intuitive to say, let those 10 things worry about their fate than it would be to, like, on the fly do surgery on my own thing over and over. By thinking of them as separate objects, I found it helpful in envisioning the solution. You may or may not feel the same way about it. So It really depends on how the problem is set up, whether you should think of it as a recursion where a function calls itself, or whether the function creates another object and does something on that other object. Okay, 4C thing link is broken. Okay, I'll deal with that. Okay, I'll deal with that in just a minute. When you guys do the lab. There's nothing I can do about this right now anyway. All right, let's go back to the lecture. Okay. Come on. Oh, what happened? Oh, it broke here. Okay, well, thanks. So, the example that's in the book to encourage recursive thinking is this palindrome question. So a palindrome is something that reads forward and backward, such as that great classic, a man, a plan, a canal, Panama. So how would you test that it's a palindrome? Well, probably what you would do if you did it by hand is you would have two pointers. You would have an index here, you would have an index here. You would check that they're the same, and then they would kind of, this one would go this way, and this one would go this way, and eventually they would meet in the middle. But I'll give you a much simpler way. So here's the simpler way of testing whether it's a palindrome. You look at the first letter, you look at the last letter. Do they match? If the answer is no, then it couldn't possibly have been a palindrome. And if they do match, then you slice them off, and you ask this guy here, hey, were you a palindrome? And if it says yes, then the whole thing is a palindrome. If it says no, then it wasn't. No loops, no worrying about indexes that go this way or that way. It's easy. And that all just because we can always assume that a simpler problem is already solvable. Now then there's a few minor annoyances that have to deal with punctuation mark. So let's say that this thing here, so it has an exclamation mark as a punctuation mark. But watch this. I'm going to say, oh, there's a punctuation mark here. Is it a palindrome? I'm just going to slice this thing away and say, is it a palindrome without? And if the answer is yes, then it's a palindrome. If the answer is no, then it isn't. Easy. So in this way, the logic of the problem becomes very, very simple. Now, that's because I had the right intuition to say, let's go to the beginning and the end and see if they match. If I had done something different, if I had said, well, let me try to cut it in half and compare like the first half and the second half, that would have been kind of hopeless. So, and I did, which is why I didn't do that. All right, so in general, the trick is how can you arrive at the simplification? So let's look at another example. No, that's 46A. So you're supposed to find an array of all positions where one string occurs in another. So over here, let me blow this up a bit. We're supposed to find the locations of ran in this here. So there's one here. And I was just about to say, and there's one here and there's one here. But that's crazy talk. That's not recursive thinking. Recursive thinking says, there's one here, and then let's worry about the rest by a recursive call. So let someone else figure out where these are, and then all we have to do is add this one index to what the other fellow did. So that's how you want to think about it. So in this case, it's a little bit trickier because you need a helper method, which we'll come to in just a minute. Okay, so this was just from the book. Now, here's the final answer to the palindrome. It does get a little long because I have all these comments in here. And here, the solution, again, uses the sentence object. And it makes the sentence shorter because I was thinking it might be helpful for people to thinking of the chopping off part as something that actually happens on an object. So we take the first and the last character and so on. You've read through that. So now I have this question. So it's always a tricky business how you should start off the recursion. Should your special case be 1 or 0 or maybe even -1 or 2? And so here I'm proposing a change. I'm saying maybe it'll actually all work out if instead of going down to 1, that 0 is our base case. And so I'd like you to answer this question and see if I'm right. So you need to look at the code and see what would happen if you change the 1 to the 0. And let me put this on Piazza. Oh. A, B, C, D. Really posted. Is it there? Stupid thing. They're not frozen. Just saving. Oh, that's gosh, I really messed this up. No. Okay, well, Piazza seems to be dying on me here, so let's just do it. So the question is, when this thing here is 0, and now I guess we need to try it out. So let's just try it out with a string of length 0. Oh, is the empty string a palindrome? Oh, yes, it is. It's the same backwards and forwards. So if we take the empty string, it'll return true, so that was fine. Now let's take a string of length 1, like A. Is that a palindrome? Yes. Sure it is. It's the same backwards and forwards, right? So what does it do? It computes first. Okay, what's first? First is A. What's last is also A. Are they the same? Well, yeah. So we go into this branch. And now what happens? So what was length? Length was 1. So our text is A. So we take the substring starting at 1 and going all the way to 0. What happens? Well, something has to happen, right? Is it going to give you an answer? So, I mean, it's going to give you like the empty string. Is it going to give you no? Is it going to throw an exception? Is it just going to shake its head and say, oh my, oh my? I mean, it has to do something, right? So it's going to throw an exception. So the way substring works is that if you give it indexes that are not valid, it throws an exception. And so the only way to answer this question here was to trace through the code. Right? There's no other way to do that. Okay, my internet connection. Okay, well, I am shocked to find that out. All right. Moving on. Okay, recursive helper methods. So it's possible to simplify the implementation of the is-palindrome method. It may not be as clear when you do it, but the code does get a little simpler by saying, let's just pass in the parameters where we're searching. Let's just pass them into the method, and that way, instead of taking a string, breaking it into shorter strings like this, it does take some computational effort to compute these shorter strings. That way, what you do is you just take the string with these indexes, and then recursively you call it with these indexes, and then you take the same old string with these indexes, and so on. So instead of physically breaking up the string, you just change the parameters and make them closer to each other. And that just makes it a little bit more efficient, and oftentimes it makes the code a little bit easier to write. So usually I like to think of the problem conceptually first, and then I say, well, do I really need to create all of these new objects, or can I use a helper method in this way? So for example, in the first homework, where you have to do something with this array, with the string, right? So what was it? Fran, ran, and ran. And so you could solve this by taking this string, finding this first thing, and then making a new string that contains these shorter things. You could make the recursion that way. But by using a helper method, what you do instead is you say, well, I'll just keep the original string, but I just have some index that says, don't look at this stuff. Only look at things that are to the right of here. And then you move that index further to the right with every recursive call. And then that way you avoid breaking up the string. The other thing that's often useful is, in this case, we have to keep an array list of the answers, right? So over here we find that 1 is one of the answers. And you could pass that array list as, you could pass an array list as the second parameter, so that over here it already has the 1, and then it just appends the 8, and then sometime it appends the 15. So you could have this little helper to accumulate the answer. So in this helper method, you would have two helpers. Helper number 1 is the index that says, don't look to the left of this, nothing happening there. And the other one is a collection that lets you accumulate the answer. And of course, when you do that, those helpers are nice for setting it up, but you don't want the user of your concoction to know about these helpers, so you want to then provide a second version that calls the helper. So when we see that on the slide here, here's the recursive helper for the palindrome. And it's not here. Okay, it would have been here. It's in your book. In the book, it shows that there's a regular is palindrome. I'll just write it up here. It's not doing it for me today. That has no parameter, and it calls the helper with parameters 0 and what I think length minus 1. So here you have the method that the user sees, and this one here is the helper. Note here that they have the same name. That's actually commonly done in languages that have overloading. Other times people call it is palindrome helper or something. And it's then just tedious because then the is palindrome helper recursively has to call the helper itself, and then you keep using that word helper multiple times. And there is, after all, a global pixel shortage, so we don't want to do that. All right. Then let's see if Piazza has recovered. In which case, let's see if it didn't. In that case, I'll just change this one to a 3. It doesn't look any better. All right. How do we save that for next time? Okay, any more? Well, I can't get to Piazza, so I don't know if there are questions. Okay, does anyone want to shout a question? The what? Yeah, I can do that. Okay, broken slides links, I'll fix that. I think I did this. Then I guess I can put the poll up here. Okay, let's try it. So, what does this mystery thing return? Get out a sheet of paper. Values start 3. What does it? Yeah. Okay, I only have 13 answers here. I'm going to wait until I have a few more. No. I can't imagine how you can do this without paper, but 26 people did. 30 people did. So let's see. So mystery A, 1, 3. The 3 comes from because its values, whatever this index was, it's the values there. So then this one must be a 1, and this one must be a 4. And then we can see, what does mystery A34 return? It returns whatever that thing was to the right. So this one here returns 4. And then we take the max of the 4 and the thing that's over here. So this one also returns 4. And then this one here, we take the max of these two, that also returns 4. And this one here, we take the max of minus infinity and 4, so the answer must be 4. And so you really need to just figure this out a step at a time. And 55 people did so that's good. All right, so it doesn't look like this is an unsurmountable obstacle. Then let's move on to the lab. So I'll fix the various links when I get back to the office. I can't do it.
So the return,
Yeah, go ahead.
the bottom return max is making a call to the method again.
Oh, yeah.
Okay.
That's what makes the call. That's, you saw me, unfortunately I can't get him back now. You saw me writing those 4 method calls. And yeah. So what you need to do is you need to just laboriously go through this and say, right now we're making the call. So mystery. I'll just call this thing A here, okay? A and 0. This is not my friend today. 0 minus infinity. And then you need to see what the heck was the call. Come on. So that calls, we're not in this case. So we're in this case, so we're now computing math max of whatever my value was, that's minus infinity, mystery of a 1, 3. And so you need to now go and find out what this thing is, again by writing out what that call is, maybe even on a separate line of paper. And then again going in here and see it calls mystery of something. And then you need to put all the return values back together. So in fact, the best way of doing this is, if you want to do it slow and steady, is you write this down. You now say, gosh, I don't know what this is. You then start a separate sheet of paper, and up here you now figure out what is mystery of A1, 3. And if you use index cards, it works very nicely. Use a separate index card, figure it on a separate card, and that way you're not distracted by what's going on this card. Eventually, you're going to find what the answer is. Eventually, it's going to say that this answer is 4 by doing it on a couple of other index cards. And it really works well with index cards. There, you can put them aside, and then once you know that the answer of this one is 4, you can put the answer back here. It's 4, and then you know that the answer of this whole thing is 4 as well. Now, in this case, you're completely done. But when you compute the answer to this, and it needs another card, you eventually need to feed it back in here. And really, if you're confused about this, get out a bunch of index cards and do it with the cards. It's well known that people learn better when they have physical objects that they manipulate. And you'll really see that it makes, that way you get this idea of this suspended computation. Really, you feel it physically because you're making this computation on this card. You have to put the card aside because you don't yet know the answer. You get out another card. You start, again, what is a pretty easy computation, and you have to set that aside. Eventually it gets so easy that you know the answer, and then you have to figure out how to put it back together. So by all means, do that so that you experience that.